similar. Similar shapes, Kyle, are very good. Just using those high-favorite words. Proportional, which means what? What's it mean for something to be proportional? Ashley?
They're like the same size amount, and like if you're gonna multiply a shape by, let's say, all the sides by 3 or something, that would be proportional.
Okay. Proportional basically means all the sides get bigger or smaller at an equal rate. I like to compare it to blowing up a balloon. Mostly balloons are proportional because as you blow them up, they expand. You know, you don't just get a flat side and the other one bulges out like that. They all kind of blow up together. Okay. By the way, similar means that they have the same shape, but not necessarily the same size. And you have to be careful when you say same shape because you can have two triangles that are not similar. I mean, they're both triangles, but they're not similar. That's because they have to go together at the same rate. They have to get bigger at the same rate. Now, let's say I have two similar triangles, and I'm going to draw them here. Triangle. Let's say I've got this triangle, and then I don't want that one. Okay, now I can see those two triangles, ladies and gentlemen, would not be similar. Okay, why? Because in order for something to be similar to this, okay, two sides would have to be very equal, and then that other side would have to be almost half of that side. So this one is not similar, but let's just say, what do you say, about something like that? Just agree with me, that's fine. Let's go with that.
Yeah.
These two are similar, and then label these sides here. Let's call this triangle A, B, C, and then triangle D, E, F. Because when we talk about similar triangles, a lot of times we talk about corresponding sides. Okay, what do we mean when we talk about corresponding sides? Basically, probably the easiest way for you to kind of think about that is think about it'd be the sides on the different triangles that, I'm going to put this in quotes because it only works so good, that match up. In other words, if I asked you what side corresponds to CB on this other triangle. Okay, what you're looking for is, like I talked about that balloon, if you blew this up like a balloon, which side on this triangle is in the same place, or would be the side that if it was a balloon would expand to be that new side. In other words, this goes like this. If you're blowing it up, these things kind of expand like that and it gets bigger. The corresponding side would be side FE over on the new side. And the answer to that would be FE. By the way, I don't believe, we can't use equal because the two sides aren't equal, are they? Kyle, are this side equal that side? No. And when you show corresponds, you put a little squiggly line above the equal sign. So this little thing, an equal sign with a little squiggly line means side CB corresponds to FE. Now it'd be a little hard to tell if I asked you what side corresponds to AC. If these two sides are in fact equal, you could say there's two answers over here because it wouldn't matter. You could say this side corresponds to that or this side corresponds to that because they're both equal. It doesn't really matter. And you can flip things and turn things when you're talking about corresponding triangles. So you could either have DF or you could have DE. either one of those really would be corresponding to that sort of thing. Got that? Another thing about similar triangles or similar shapes, if shapes are similar, okay, if shapes are similar, if they are similar, oh great, I gotta put somewhere else. If similar, they have equal angles. Okay, in other words, if this angle here is 20 degrees, the corresponding angle on the bigger one will also be 20 degrees. Okay, if this is, let's see, if these two angles were equal, 21, 20, if this is 80 degrees, then its corresponding angle is also 80 degrees. Okay, so similar shapes have the exact same angles inside them. The side lengths are different, but their angles would have to be the same. Okay, it just uses that angle, but it gets bigger, and they all get bigger proportionately. For example, what else do they ask us about this? I should maybe have you look in the books. Take a look at page 232, will you please? 232, example number 2. You're given a triangle that looks like that and a triangle that looks like this. It's a 3, 4, 5 triangle. And a 12, 15 triangle. And then they say this is X. And this is important to note. Are you looking at example 2 with me? What's the first 5 words say? These triangles are similar. That's important to know. Why? Because what does it tell you? It tells you that the sides are proportional, and it tells you that their angles are equal. Okay? If this was 40 degrees, then this would have to be 40 degrees. If this is 90 degrees, this is 90 degrees. If this side up here is 50 degrees, this side is 50 degrees. All the angles have to be equal with similar ones. Now, the important thing is they're asking for side X here. Kendall?
It's 9.
We haven't got to that point yet.
Oh.
Work with me and be patient here. Okay? And like Ashley said, okay, if the sides are proportional, she said something about, didn't you say something about if you multiply 1 by 3, you have to multiply everything by 3 or whatever? Okay, if you look at this side, which corresponds to this side, what did you do with 4 to get 12? You multiply Alex by
3.
So that means every other side, in order for it to be proportional, every other side would also have to be multiplied by 3. So 5 multiplied by 3 was 15. And to find X, you would just take 3 and multiply it by 3, which is what, Kendall?
9.
Is that what you said?
Yeah.
Okay, so X would be equal to 9. If corresponding parts are similar and proportional there. All right, take a look at example number 3, because this is the real world here. You with me, Josh? This is on top of page 233. Oh, by the way, sorry, let me jump in and come back to this one here. When you do this, what we just did there, that little thing, write this in big letters, is called the scale factor. If I gave you a nickel for every time in the next year and a half that you'll hear the word scale factor, you would probably have enough to buy a couple peanut butters. Not much. Scale factor just is what number do you multiply one by to get to the other one. That is scale factor. Okay, now with that being said, let's look at the next example there. It says an architect makes a scale drawing of a building. Why, if you're drawing a building, when you look at a blueprint, why do you need to scale it down? Why not draw blueprints the same size as the building, Gabby Parents? It would be a very large piece of paper. And if you had to, how would you carry this large piece of paper if you actually had it the full size of it? You'd probably have to rent a truck that had a big long, like a tractor trailer. And who wants to rent a tractor trailer just to carry the plans? So, in order to draw plans, we say scale it down. And that's the same thing as scale factor, and that's what this problem says. If 1 inch on the drawing, 1 inch on the drawing equals 4 feet on the real thing, they want you to know what is the scale factor. What is the scale factor? Now here's the deal. Okay, you're not going from 1 inch to 4 inches, you're going from 1 inch to 4 feet. In order to get the scale factor, you're going to have to say how many inches this is. 4 feet is how many inches, those of you who are Einsteinian sort of people there. Taylor Pavia?
48.
Very good. So the scale factor is, what are you multiplying everything by? 48 is your scale factor. Because everything from the model is 48 times bigger on the real life thing there. And then the next question is, what would be the length of a room that is 5 inches by 4 inches? What do you suppose you're going to have to do there? If this is a problem you were assigned to tomorrow, what do you suppose you're going to do? First thing, Nate, you're going to sketch it out. Thank you very much. We've got a 4-inch by 5-inch room that we want to know how big the real life thing is. Okay. Now a couple different things that you can do with this. Okay. First of all, you know the scale factor, right? Yes, you do. What's the scale factor?
48.
Okay, 48 inches. So that means you're going to have to multiply everything here by
48.
times 48 here to get to this new one, and times 48 here to get to this new one. Now, if you think about this just a little bit here, because you're going to multiply it by 48, you're going to get what? 48 times 4 is, somebody got it, 192 inches. Now, do we ever say anything's 192 inches? No. Which means you're going to have to do what? Right, change it back into feet, which means you're going to have to divide it by 12. Now, stop right there because you're going to save yourself a whole lot of work by just multiplying. Okay, this is your scale factor. But if you're just looking for the new measurement, there's no reason to multiply this by 12, get 48, get the answer, and then divide by 12 again. You're just doing something and then undoing it again. The answer would be the same as if you took 4 inches and multiplied it by 4 feet. You know what I'm saying? If 1 inch equals 4 feet, let's do it like this. If I made a table, children, and I said 1 inch equals 4 feet, 2 inches is going to equal how many feet?
8.
3 inches is going to equal, and 4 inches is going to equal 16 feet. So if you're just going from a scale drawing to a real drawing, okay, you don't have to change this into 48 and then change it back into feet. You can just say, well, I know if 1 inch equals 4 feet, then 4 of those is going to just equal 16 feet, which is what this is. If you would divide this by 12, you'll end up with 16 feet again. Same thing with 5 feet. I don't have to multiply 5 by 48 and get 220 and then divide by 12 and get whatever. I can just take 5 feet, multiply it by 4, and get how many feet? This is going to be a 20-foot building. Okay. because you're just doing something and then undoing it. Okay, if you're talking about scale buildings, you can look at it like this. You could make a little box. You talk about ratio boxes. I think I got in trouble with that before. Okay. You could just do it just like this. The scale building is 1 inch equals 4 feet. So if you have 4 inches, what are you doing? You're just multiplying by 4, you get 16 feet. You can just make a little ratio box and it's all going to be good. And I can tell that's going to scare you there. Take a look at, flip the page there. Let's do a little bit more on that. Page 234. We'll walk through a couple more of these here. Looking right there at the problems H, I, J, and K. What does it say? Draw 2 rectangles, one 1 centimeter by 2 centimeters. 1 centimeter, I'm just going to do it up here, you just listen. 1 centimeter by 2 centimeter, and the other one is what? 4 centimeters by 2 centimeters. 2 centimeters by 4 centimeters. This was a 1 by 2, and this was a 2 by 4. Oh, 2 by 4. What is the scale factor then? What are you doing with each side to get to the other one? First of all, are these similar? They absolutely are. How do I know, Ava? Because
they both can, like, well, you can multiply it to.
scale factor is what?
It's how much is,
What is the scale factor? I'm actually asking for it.
Oh, it's 2.
2. You know they're similar if you multiply this by 2, you get the short side. You multiply this by 2, you get the long side. So the scale factor is just times 2. We call that doubling something, right? Now, here's an interesting thing, and this is your introduction here. And I think we talked about this before. Maybe we didn't. Did we ever talk the pizza thing?
Yes.
Yes.
Now, perimeter. What's the perimeter of the small one? 1, 1, 2, 2 is?
6.
Perimeter of the small is 6. The perimeter of the big, you would think since you're doubling it, the perimeter is going to be? And that is in fact the case. 2, 4, 4, 2 gives you 12. 8 plus 4 is 12. Now here's where you have to be careful. That doesn't work with area for the same reason as our whole pizza situation there. I hate to go back there, but the book, you eventually, we talk about this in 8th grade on a daily basis for the last couple weeks there. Okay? The area of the small one is 2, correct? 1 times 2. Now you would assume that since you doubled the dimensions that the area doubles, and that is not the case. Okay? What actually happens? The area of the small one is 2. The area of the big one, ladies and gentlemen, you can do it, the math right there, 2 times 4, Alex, is 8. In other words, the area actually quadrupled. And the reason for that is, children, see if you can catch on to this, some of you will, some of you don't. You don't have to if you don't get it, it's fine. The reason is when you find area, what do you multiply by? Length times width. Okay. What happened to the length and the width and the bigger one? The area of the bigger one, you doubled, did you double just the length? No, you doubled both the length and you doubled the width. So that would mean for the area of the big one, you have 2 times the length and 2 times the width, which gives you 4 times bigger when you multiply the length and the width. Okay, and that's why this is 4 times bigger, because you multiplied 2 measurements that were doubled, not just 1. Okay, and here, when you find perimeter, you're not multiplying by anything, you're adding. That's why it doesn't change, because each one is just added together. But when you multiply, and the same thing with volume. When you do volume, what's the formula for volume?
Length times height times width.
Length times width times height. If you double something's dimensions, you not only double the length, you double the width, you double the height, guess how much bigger something is in volume if you double it?
8.
2 times 2 times 2
Oh.
is
8.
8 times bigger. If you could order a pizza by volume, and you could double the volume, if you doubled its dimensions, you'd get 8 times more with that double pizza than you would with the other one. If you could do that. Kendall,
So you don't like, however, like, it's like, cause it's 4 times the width is like.
if it's area, it's gonna be, if you, and here's the deal, here's what you have to understand, Kyle. If the scale, it all depends on what the scale factor is. If the scale factor is times 2, then the perimeter will be times 2, but the area will be times 4, and the volume will be times 8 times bigger.
So you don't like actually get the area or volume, you don't multiply it by the width.
But we're not, don't worry about that just yet. But let me throw this at you, those of you that picked up on that there. What if my scale factor was 3? How much bigger would the area be? And how much bigger would the volume be? If you use the same thought we did here, if these were not 2's, but it was 3 times bigger and 3 times bigger here. Colton, the area would be, nope, 9 times bigger, because instead of this being, the length is 3 times bigger, the width is 3 times bigger, that gives you a 9 times bigger object. And up here, if it was 3, Sam, it'd be 27 times bigger. You don't have to know that. If that doesn't get there, don't worry, we'll hit that 1,000 more times. Taylor.
Okay, so how come just length and width is 3 and how come volume is times 3 for each one?
Wait, how come length and width is times 3? It is. You should have 3L, 3W, 3H, and that's where 20, that's where the
I thought it
27,
was 2.
that's where the 27 came from.
Oh, so they're both 3 times 3.
Yes, if this was 3, you change them all.
Okay.
That's neither here nor there.